So, does anybody want to ask some questions about what's going on? All right, so first questions, are the slides up? No, because I'm super behind today. They will be up at some point after the lecture, and I apologize for that. So question about should we use Data Hub or your own server? I think it depends on what you're doing, right? Chase raises an excellent question about like, if you go last minute, everybody's going to be on Data Hub and you'll have less resources than you would if you do it right now. So if you have, when you say your own server, if you actually have a good server, if you have some sort of nice system, it could definitely be worth your while. So if you don't, I definitely recommend getting a start on Data Hub and potentially on Google Colab and potentially doing both at the same time. And maybe some of your project on one and some on the other, kind of splitting up stuff. You can always start multiple instances, right? These kinds of ways, these kinds of things are ways you can get around the limitations. Use as many different resources as you can. The only problem with that is keeping track of what you did where and integrating it all at the end, right? We're talking about final project, Phil. So homework 6 should hopefully not require those kinds of resources. On my computer, which is a 2017 era iMac, it took about a minute to do the computations in homework 6. So hopefully you don't need massive computation for that. I'm curious about Chase saying that GeoPandas is impossible under Anaconda. I didn't know that. So what's the dealio there? It's funny. So I last used GeoPandas about in 2019, and it was definitely on an Anaconda install, and it definitely worked. So could just be something newish. All right, I love that people are throwing up stuff about which solver to use for homework 6. There is definitely an element to finding the right solver. And you will get different solutions with different solvers potentially. Hopefully they're not going to be very different, but a little different. So, all right, ladies and gentlemen, and people of all shapes and sizes, I just want to go ahead and get rolling unless we have very specific questions to address. Okay. So what we're doing today is we're finishing up in looking at the kernel trick of support vector machines. And I wanted to last time just remind you that we started with the ideas of k-nearest neighbor, right? Because k-nearest neighbor, it turns out, is a good way to think about the kernel trick. So when you have a situation where you have data points and you know the labels for those data points, you can use the data points themselves as the labeling system, as the algorithm, right? So in one nearest neighbors, anything that's closer to a particular dot is going to get the same label as that dot, right? And when you generalize that to k nearest neighbors, you use the 7 nearest neighbors to determine what's going on right here. You take the highest vote, the most common vote of the 7 closest items to that point, and that gives you the label for that point. Okay, so that relies upon a distance metric, right? So some metric of similarity, all right? We have typically in a k-nearest neighbor situation, we'll be using the Euclidean vector, but it could be anything, right? You could use all sorts of different norms. anything that is a metric function that meets that definition can be used in a k-nearest neighbor situation. Okay. So here's where we left off the other day, with the idea that if we have a new data point, we might want to classify it just like in a nearest neighbor situation. Okay. That if we want to know how to label this one, we might try to figure out a similarity metric, right? So if we're going to create the similarity of X to one of these data points, okay, then we might, for instance, write this as a Gaussian similarity, okay? And the reason I'm using that, for instance, is of course that this is a very common way to use support vector machines. So that similarity would be something like the exponential of the norm between this data point X and one of these landmarks, right, that we have defined, and put all that over the standard deviation of this Gaussian, right? So anything that has this shape of an exponential to the minus some value over the sigma squared, you know, that has the beautiful shape of a Gaussian curve. And somebody didn't like my one-dimensional Gaussian from before, right? So what if we if I try to draw this in 2 dimensions? So around L2, right? Here's my beautiful 2-dimensional Gaussian that I'm trying desperately to draw for you, right? So the nature of a Gaussian curve, when it's defined like this with a single sigma, is that it's equally round, so to speak, in all dimensions, right? So it's going to fall off in the same speed this direction as it will in this direction, right? So it's round in any cross section, right? So, all right, this gives us a similarity score, right? And things which you are far away from and well out in the tails on, right? The similarity, oh my goodness, my little Apple Pencil is dying. All right, so the similarity of this data point X and L2, I keep switching whether that's an upper or lower, sorry people. Let's get rid of that and let's do it all consistently. So the similarity of our data point in L2 is something close to 0 because we're well out on the tail over here. And if we, make this kind of Gaussian out here, and again, I apologize for my 2-dimensional Gaussian drawing, then the similarity of X and L1 is maybe something a lot bigger than that. Maybe it's, less than a large number, but it's, it's something much bigger than 0. So let's just say that this is approaching 1. Okay. So if we want to describe where X is in relationship to all these similarities, we can do that. And we can use that kind of a formulation in terms of finding a support vector, all right? So now, I think that Kylie has asked the right question here. How are the landmarks chosen? What are the landmarks that I'm talking about? Well, in fact, Kylie, to give away the whole plot line here, those landmarks are the training data themselves. So what we can do is, just like k-nearest neighbors, we can use the training data as landmarks and take new test data in and look at it in terms of how close it is to each one of those training data, exactly like k-nearest neighbors, but with a subtle important improvement. Okay, so now that we know that's what we're going to do, let's imagine that we have these similarity functions, which now I'm calling f. Okay, so each one of these, f1 is the similarity of x and landmark 1, and f2 is likewise for landmark 2, and so on and so forth. So now what we can do is we can take the location of x with its similarity metric to each one of these landmarks and use that as the decision boundary. Okay, so we're going to predict 1 if and only if we go over a threshold on the summation of all of these similarity measures. Okay, so we could pick a set of thetas of these parameters, which enable us to set the optimal decision boundary. Okay, so these thetas are now the equivalent of a weight vector, right? These thetas are the dials that we're setting to make x come out to be the right prediction. Right, so these thetas, we could also, in our previous notation, we've been talking about those as weights. So what does it mean to have a setup like this, right? So if we have this first theta, right, which is like a bias term, it's the W sub 0, right? And it roughly saying the relationship between that one and any one of the others is going to set how far away you have to be before the decision boundary kicks in, right? So if this is set up such that, this is the distance 0.5 in here, then the decision boundary would stretch out in a perfect circle of that radius for that one particular landmark and only that one landmark. Okay, so if we have that same circle, sorry, I can't draw it all today. All right, I'm trying to draw the same radius there. Then what's going to happen is actually the intersection between those, right? So the decision boundary is going to be the intersection between those. Okay, and note that here the parameter on that is 0, which means that this must be a negative, right? This is the negative classes out here, and these are the positive classes in here. So as a concept of a decision boundary, which is lying on an exponential kernel on everything. Sorry, okay. Anya has quite rightly called me out for misusing the intersection. I should have said the union. Yeah, so the union between those two situations, right? The entire part of it that is in one or the other, that is what I should have said. I incorrectly said the intersection. Awesome. Thank you for that correction. So yeah, there we go. This is the idea of how you can set a decision boundary in a nonlinear way using a Gaussian kernel. Okay. So let's think for a moment how this is similar to and different than the k-nearest neighbors setup. Right. So why don't you guys tell me, actually, well, I'll let you talk about what is the same as a k-nearest neighbors thing and what is different. Go for it, anybody. Let's start with the metric space. So k-nearest neighbors typically has what kind of metric space? What kind of a similarity measure? What kind of distance, particularly? Euclidean, exactly. Is this one using the Euclidean distance? Yeah, so it's a modified Euclidean distance, right? So there's a Euclidean term here, but it goes through a nonlinearity. It goes through an exponential, right? So this Gaussian similarity measure is based on Euclidean distance, but it's a nonlinear transformation of it, okay? So not the same, but based on Euclidean distance. All right. Okay, what's another thing which is a little different here? Anybody want to articulate why I just scrolled around those ones?
The weights?
Not the more parameters, but no. Okay, so so what I'm getting at particularly is that when we have parameters where we can weight the importance of any one of these landmarks, right? So, you know, these two landmarks are both a positive case, and this one's a negative case. And in a regular k-nearest neighbors, you would just have that, you know, set up where we had whatever, here's our data point, and we'd look and see whatever's in the neighborhood and count up the votes, right? And each one of them is going to count the same. But now what we have is we have a weighted situation where some of them might count and some of them don't count at all, right? And we would have potentially different weights for different landmarks, right? So when you're closer to a landmark, you're going to have more effect to that landmark than you are from this one far away. Okay, so even within a neighborhood, inside the 7 nearest neighbors, you would have counted all the votes equally. In this formulation, we count the one closest still in the similarity measure more strongly than any of the others. And potentially we can set these weights so that these weights override. So that's that term, right? That has the similarity measure so that the ones that are closer are more important. But these weights can override that. These weights could mean, you know, some of these landmarks we don't care about. And this weight could mean that some of these landmarks are highly, highly important. And our training algorithm is the one that's going to update these chosen landmarks, right? Sorry, I'm misunderstanding Chase's question, I just realized. It's going to update these parameters, these thetas, to pick what are the right thetas to do this job. Okay, so, and Chase, in answer to your question, the training is not choosing the landmarks. The landmarks aren't changing. The landmarks, in fact, are all the training data. And we're going to get to that in just 1 second. Okay, so let's take a look now at some of the, so one thing that I haven't talked about at all is one of the great things about this, if you realize it, is that it's really just another kind of transformation, right? So we saw earlier that if you take, you know, we have some sort of data that we want to fit a nonlinear curve on, we can take this linear x value and we can transform it, right? We can do a polynomial transformation. We can turn that into 1 plus x squared plus however many polynomial terms we want, right? And by transforming a single linear variable x into this polynomial feature space, what we've done is we've blown up what was a one-dimensional problem into, if this is an m-dimensional vector, into an m-dimensional problem, right? Okay, and by doing that, we enable a linear algorithm to fit a nonlinear curve. So that kind of feature transformation is exactly what we are doing here, right? We are transforming the features. But if we do it the normal way, we have this problem. We go from 1D to MD, and m-dimensional problems are always going to be harder, right? Think about how we were talking about k-nearest neighbors, and it suffers from the curse of dimensionality. Remember that? When it suffers from the curse of dimensionality, stupid thing. All right. That's what I wanted, right? That when we blow up to m dimensions, to a large dimensionality, our data points don't cover that dimensionality well. So we need exponentially more data points in the higher dimensions, and that is a problem. Well, so k-nearest neighbors suffers from that because it operates in that polynomial blown up feature space, right? If you're going to do that kind of trick. What SVM does is it operates in the original, or so the original space is just a few dimensions. Let's call it this. Sorry, I'm getting mixed up. Let's call this original dimensional space d-dimensional. Okay, then in that original d-dimensional data space that the inputs come in, SVM doesn't blow it up to d to the mth power, which would be what would happen if we made this kind of polynomial feature transformation. What it does is it just brings it up to d squared. Okay. So now we increased to a square, but it's not as bad as a to the m power situation. And that saves us computation time, and it saves us on the curse of dimensionality. All right, so this is the foreshadowing of how this all works, of why the kernel trick is a fairly awesome trick. So actually, let me go ahead and bring it all down, right? So what we were showing was this idea that if we have something which is truly a nonlinear decision boundary that we want to do, we can take what was a linear variable and transform it, right? We can do the polynomial feature trick. Okay, so we took this singular x dimension and we've turned it into a polynomial feature set, which has, so it was x1 and x2, and then we can transform that into x1 and x2. Those are the linear features, and here are the polynomial features. Right? We've blown it up, made it a bigger thing, right? And if you wanted to try to understand what that was doing, that would be essentially pulling out a third and a fourth dimension, which are stretching out this problem. And we'll see a visualization of that in a second. Okay. So you've seen the SVM formulation before. All right. This is just a slightly different way to write it that I'm stealing from somebody else. Okay. So this is, right. So that is the weight squishing margin term. And this one here is the misclassification error term. in terms of those size, which are the slack variables, which allow us to have things that go over the margin a little bit. Okay, so this whole thing, and ignore the exact notation, but this is the nature of the support vector machinery in the linear space, is called the primal form. This is the regular old loss function, right? So the thing is that the way solvers, various numerical solvers, actually solve an SVM loss function is not this way, because this way is just as slow as everything else, right? You have to explicitly do this solution in the number of dimensions that are here. So there's a very useful property of this math, is that it can be converted using something called a Lagrangian into a second or dual form of the same problem. And what that dual form lets us do, and I'm going to skip all the math because this is not a class about how to do optimizers, okay? What it does is it enables us to just realize that the solution, that the minimizer, the weight vector, is just a linear sum of the data points themselves. That's our training data in there, okay? Like, think about the fact that that the partial of this has those terms in it, right? It's proportional to that, right? That's one of the terms in it. So I'm just kind of giving you a hint of how this derivation works, because I definitely do not want to go through the whole derivation. It's beyond the scope of this class. But so this is the end result of it. This is skipping all the cool stuff. That the dual form enables the solver to just look essentially for these alphas. Okay, once we've determined this coefficient alpha for every data point in the training set, then we know the solution to the support vector machine. And in fact, more generally, what happens is all the solutions that have non-zero alpha are the support vectors themselves. In fact, that's the very definition of what a support vector is. The support vector are those data points where the alpha term is non-zero. Okay? So the trick that we're going to get to, and I know I'm kind of giving this at a super high level right now, is that when we do things in kernels, when we make a kernel transformation, we're not going to actually transform into that high dimensional space. We're going to take, just like we just saw, remember that the training data is the landmarks, okay? So the kernel itself is defined as something which has an inner product, right? A dot product, okay? But an inner product is this particular generalization of a dot product, okay? So anything which is a kernel is something which we can write down as a dot product, okay, of this kernel function phi, all right? So if what we're going to do is we're going to take the dot product between two data points, right? These are just any two data points. So we're going to do this for every possible pair of points, x and z, right? And the formulation of the kernel trick is exactly like what we saw a second ago in the dual formulation, that it's just the data points themselves, a sum of those data points multiplied by alphas. But now instead of the data points originally, we have the kernel transformation of that data point with respect to another one. Okay. So we create this higher dimensional mapping, but the higher dimensional mapping is only between all pairs of points. Okay. So if you're going to do some really high dimensional kernel, which would go much higher than a squared of something, you're still only at a square because you're just doing data point 1 versus data points 2, 3, 4, 5, blah, blah, blah. Okay. So the overall dimensionality is now just something like roughly n squared, but more particularly, it's like n minus 1 over 2, right? Because it's like an upper triangular matrix for those of you who are thinking in those terms. Okay. So I'm going to go back in and fill all this in later. I was originally going to do a demo first before I went to this, but I feel like it actually makes better sense to give you the full example first. So there's a question here. So the phi function, Anya, represents the actual kernel. Okay, what the kernel is that transformation, right? So so if we're going to do a Gaussian, right, this kernel phi is the Gaussian. All right. So maybe at this point, I should actually head to the Jupyter notebook to start to fill in these ideas. Okay. So let's get that guy in there. Okay, can everybody see the notebook? No, you cannot see the notebook. Yep, okay. Okay, great. All right, so conceptually, I realize this may be a little confusing. And if you have questions, please do pop up with them, okay? This is one of those things that's going to require going over this again and again to get a hold of it. So this notebook is going to go up on the notebook's GitHub. So you will be able to play with it yourselves. So we're already familiar with the generic idea of the linear support vector machine, right? We've got some data points, and we want to draw some line in between that best separates these two kinds of classes. And we know that if we draw a line that looks like this one, that's maybe suboptimal in some way, right? And the intuition, again, is to maximize the margin. So if we have some new data point, right, by this red X, that it falls on the correct side of whatever we need here. Okay, so what would that, what would that look like, right? Where the margin is the space in between the closest data points that are set, the distance that goes between, perpendicular to the decision boundary. So the distance defined by the weight vector, right? The thing that the margin for any given one of these decision boundaries is the space in between negative class closest point and the positive class closest point, perpendicular to the decision boundary that's drawn. So this bad decision boundary here has a very narrow margin because the distance perpendicular to the decision boundary is very small between these 2 points, right? So that's just like linear support vector machines, the ones you've already seen a couple of times now. Okay, so for those of you who are wondering, this is how easy it is to do a support vector machine in sklearn. Okay, so that's how you define one. It's got a particular C that we gave it, right? And there's a bunch of other stuff in here. Important to note is that the default kernel is the linear kernel. So when you just call a support vector classifier like this, you are getting a linear one unless you tell it to use a different kernel. Is it not RBF? Probably Gaussian. My bad.
You're repeating the argument twice. You have kernel twice.
Oh, thank you. That's what's going on. You're the best. There we go. So now we have a radial basis function, that Gaussian kernel. Okay. All right, so that doesn't matter. Let's just get this. So, no, oops, it did need to be redone. There we go. Linear. Okay, so this is the fitted support vector machine, la-di-da, and we're plotting the support vectors, right? We need to have, the closest points that are defined, and that is where the margin is going through these vectors, right? The closest vectors, the closest data points on each side of the dividing line. Those are the support vectors. And as I've kind of hinted at already, so in fact, yeah, so this has been a question that's come up a few times, right? We need to know we need two at least to define the line, right? So the lines are all parallel. So we need two on one side at least in order to define this line. Okay, so now we know from what I kind of ran through earlier is that, in fact, the way the solver is dealing with this is it's doing that dual formulation where what it's optimizing is for the weight vector to find alphas only for non-zero alphas only for these support vector points. And all the rest of these data points in the training set are going to have an alpha of 0 and not contribute to the solution. The solution is uniquely determined by these 3 points, and you can see that geometrically, right? These 2 points define the direction of the line of the decision boundary, right? And the margin size is determined by this horizontal distance perpendicular to that line. So you can just see geometrically that the entire solution to this algorithm is representable by those 3 support vectors, okay? And that's why all the rest of these data points don't contribute to the solution. Does that make sense to people geometrically, that kind of an intuition? Questions? Yes, Kylie asks the right formulation of this. So we're going to have, right, remember that the formulation here, annotate. Remember that the formulation here is that essentially it's got an alpha, y, x for all data points. And I'm leaving out a lot of detail here, right? That is the thing that's being optimized in the dual solution. So for all these data points up here, this alpha is going to be 0, and it's not going to matter. We're going to be optimizing over it because it's one of the data points in the training set, but it's going to not matter in the end, okay? So after training, we're going to be able to ignore all these alphas. And during like a production situation where we were trying to use our classifier to predict new data, the only things we have to keep track of are these 3 data training support vectors, right? And we can find out whether something is on the correct side of the boundary using these 3 data points. So it's highly computationally efficient when we are predicting, right? And it's not bad because it's just order the number of data points when we're doing the solution. Okay. Right. So let me get back to annotation. Okay. So whatever. Here are the XY values for those support vectors. Inside sklearn, it stores the support vectors for you if you would like to see what they are. Right. So another nice thing about all this is that the support vectors being the only important points means that this is relatively robust to resampling, right? So as long as you end up resampling those important points, you're going to get the same solution. So here we just created 200 data points in the blob in the training set, but we only used the first 30 data points, and then the 60, and then the 120. Sorry, I just realized I should clear these stupid annotations. Okay. Right. So here we only had 30 out of 200 data points, and we got a kind of off-kilter solution. But as soon as we got to 60 of the 200 data points, we were getting the right support vectors, the same ones that are the actual support vectors for the entire training data set. So as long as we get the right data points in a resample, we're going to get the right solution. So, like, this situation means because support vector machines only care about the true support vectors to get a good classification, as long as your random noise that's going on in the system is not giving you false support vectors, then the system is still going to predict well. It is relatively good compared to many other algorithms at rejecting the effects of noise and randomness for those reasons. Okay. All right, but what we really wanted to get to today is what happens when we create nonlinear systems. What if we create a problem which is not linearly separable, right? Trying to fit a linear support vector machine on it produces bullshit, as you would expect, right? Because you cannot draw a line to separate positive from negative class with this. But we could, in fact, project this into a higher dimensional feature space, just like we keep talking about, right? If we produce a third dimension, we can project these orange data points upwards, right? So if we just create some vector, which is an x squared here, right? A polynomial projection at a third dimension, then we get this. Okay, let me make this just a little bit bigger for people to see. So we've created this third dimension, this r squared, right? And it has projected the orange data points upwards compared to the blue data points. So with this kind of a polynomial projection, what we can do is we can draw a linear decision boundary now, right? We can just come in here and separate positive from negative class with that line. Okay, and this is the intuition why blowing up to higher dimensions solves the problem, right? Remember the exclusive OR problem, right? That's our classic not linearly separable problem, right? If this is variable 1 and this is variable 2, and our exclusive OR is, this is not an exclusive OR, this is, right? And this is not. So you can't draw a line, a single line, but here is my terrible three-dimensional version of the exclusive OR. If we keep the not exclusive ORs on that one, and we bring the yes exclusive ORs forward into this new dimension that I drew, right? Then you have a separating plane that can drop in between them. This is supposed to lie in the middle between those. Sorry, my 3D drawings are crap, but do you guys get the idea, or am I being totally unclear here? Silence. All right. Great. So at least some people are getting it. And if it's not clear, we can talk about this again another time. Okay. So by projecting these upwards into a higher number of dimensions, we are getting separation. And at the very least, you can see it immediately with this polynomial projection, right? From this two-dimensional case to this three-dimensional case. It makes it easy to draw a linear decision boundary. Okay. So guess what? A radial basis function can work here too, right? So what the radial basis function is doing is different than the polynomial projection we just saw right here, okay? What the radial basis function is doing is it's saying, remember, if we go back to the drawing I made, probably just easiest for me to redraw, right? Here are our landmarks. And something like this, right? And we have some decision boundary, which is formed from a linear combination. Ignore that, that didn't happen. From some linear combination of these Gaussians operating around these data points, right? So that's what happened here too, right? These are the picked support vectors. And there is some linear combination of the Gaussians operating on each one of these data points, which is defining this boundary right here. Okay. Does that make sense to people? No. All right, let's try to pick apart why it doesn't make sense. What is not happening here for you? Like, what does a radial basis function do? Well, remember that a radial basis function is annotators, right? Draw. Thank you. So a radial basis function is just that Gaussian, right? So that is an exponential minus the distance of x minus this landmark point, right, over sigma squared. Okay. So what are the parameters here, right? There's a distance term So the further you are away from this given landmark point, right, the less similar you are to that point. The closer you are, the more that's zero, right? So if we have a brand new data point that falls right here, it's going to be basically this exactly the same as that data point. And this is going to be a small number, and the exponential of a very small number is close to 1. So this is going to produce a similarity score of 1. Okay. And if our data point was way over here, it would be far, far away. This distance would be a large number, and the exponential of a large negative number is close to 0. So this has got a similarity of 0, right? And if you remember that we set up, so if we set up the decision boundary is a linear combination of the radial basis scores with respect to every support vector. I mean, originally to every vector, but our support vector machine sets the alphas on all these guys to 0, right? So we don't have to care about any of those. And all we have to care about are the support vectors, right? So the decision boundary is a linear combination of the similarity scores to all of these support vectors. Okay.
Could I ask something about the other dimension?
Mm-hmm.
So all of these like orange and blue dots are the training data, correct?
Correct.
And so if we're projecting them into like from 2D to 3D, what does that third dimension like mean in terms of the training? Like, does it mean anything? It's like, how do we just like make up another dimension?
So in the polynomial case, it has a clear interpretation, right? So, so this situation, if we create a polynomial kernel, which we can do, by the way, we can solve this with a polynomial kernel too, then you would end up having the interpretation that we have physically in this drawing here, okay? So let me very quickly. Is it order? What's the, oh wait, degree, sorry. Well, I should spell degree right. What did I do wrong? Polynomial. Is it just poly? There we go. Okay, so let me clear my drawings. So this is forcing the support vector machine to use a polynomial kernel of degree 2, which is exactly what we drew here, okay? And so this physical interpretation is the one that makes the most sense to you, Yana, because we can see it. Here in the art radial basis function form of it, right, we are getting something different. We're getting the similarity between every pair of features, right? So what's happening is the similarity is being calculated between every data point, like let's just start with this one right here, and it's being calculated to every other data point, okay, in the whole training set. And those similarity metrics are enabling the solver to find those ones which are the minimal set, which can separate out the two classes. And to really fully pull that out mathematically requires going all the way through the Lagrangian math, which I don't want to do at all, and certainly don't want to do off the top of my head where I will get it wrong. But that's what's happening, right? We are calculating the pairwise similarity of every single data point with every other data point. And doing that solution, which is order n squared, in terms of the number of dimensions we get, is going to enable us to find the support vectors. So it's a harder interpretation, but I don't know if I've helped you at all. What can we go from there?
I mean, I'm confused about how the RBF. I mean, and I'm confused if it's like the same as the 3D, like 3D interpretation. I guess not, because this is using the radial basis function. So, and then the points that the model selects are just the points that make the most sense with, like, I guess, the least error.
Yeah, exactly. So we're optimizing that summation of the solution, the alphas times the data points, right?
Mm-hmm.
Okay, which is, again, beyond the scope of this class, but provably the dual formulation in the Lagrangian is equivalent to actually optimizing the loss function that we're more used to thinking about, okay?
Oh.
Okay, so that's the whole point. This crazy Lagrangian math is provably the same problem as optimizing the loss function. And therefore, we can optimize this dual form, which is really just about finding these support vectors, finding the non-zero alphas, okay, that finding the best set of points to make non-zero, right? That's really the formulation here. The set of data points that if we make these the ones that are non-zero, that we get the lowest error rate. And also the other part of the maximizing the margin part is also part of it. Okay.
Mm-hmm.
So I realize that I'm asking you to accept on faith because I cannot show you the Lagrangian math, but trust me that this dual formulation shows it. And what you get out of all this stuff, and we are running so long, what you get out of all this stuff with the radial basis function is that you're looking at the similarity between all pairs of data points, X and Z, okay? So your number of dimensions here is going to be, again, if there's n data points, you're going to get roughly n squared dimensions, n squared variables, okay? Which is high dimension, higher dimension than you started with, which was just 2 dimensions, right? But it is not blowing up to the dth dimension, right? It's only going to the squared. If you were going to actually physically project to higher dimensional spaces, then you would end up going to the dth power, right? So let's go up to this case here, right? So we took a 2-dimensional case and we exploded it to a 3rd dimension. But remember that what you would have to do in a more general case, right, is if you had, right, so if you had, say, 100 dimensions of data, right, and you wanted to do all possible polynomials of 100, right, what you'd be doing is, right, x, so you'd have, 1 plus x plus x1 plus x2 plus ... x100, right? There's your original dimensionality, but now you're going to have to do x1, x2, x1, x3, ... up to x1, x100, Now you have to do the same thing for x2, right? Dot, dot, dot. And the same thing for x3, dot, 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 right? And so you can see that the dimensionality of this is atrocious, right? Starting with a 100 variable inputs, which is totally normal for machine learning, right? 100 variables. And then you wanted to do a polynomial just up to the squareds. And now you're at 100 times 100, okay? So your dimensionality has gone ridiculous. So the kernel trick, and we are so past time, I apologize. The kernel trick is that instead of doing it on the projection in dimensions, we do it on the data points, not the variables, but the data points, right? So radial basis function is just that we have to calculate in the original dimensionality all possible pairs of distances. And then we select the support vectors. And then once we have the support vectors, all of our future calculations are just on this small number of support vectors in a low dimensional space. But yet this is equivalent to projecting to that polynomial space. Okay, we're definitely going to have to do more of this later.
I just have
So,
a quick, can I ask a quick question?
yeah.
So I'm just curious why with the RBF, why it requires more support vectors than with the polynomial, or does that have something to do with the number of degrees we give the polynomial?
I mean, okay, so yes and yes. So what's happening here is that as so in order to make this decision boundary, these are the minimum number that it needs. Because remember, this is a linear function of similarities of each one of these data points, right? I don't know off the top of my head the right intuition for how the number is falling out of the dimensionality. I rather suspect that because things are, yeah, actually, I don't know how to explain that. So I should hold off and not say that I know. But
okay, thank you.
I'm just going to confuse the situation. But remember that what's happening here is a linear combination of similarities here creates this line.
Cool, thank you.
Could I ask
Okay.
if I'm understanding correctly?
Yeah.
So the kind of point of showing the 3 dimension and then the radial basis function is that we could do the expanding, as you said, variables, which is like expanding, like adding more dimensions to see the data differently, but that gets too large, as you mentioned. So we could just expand, as you said, on the points, which I guess, is it correct that I'm interpreting it as like expanding the connections between points? Like we're just going to be looking at all the pairs of points in our training data instead of expanding on the variables.
So you can do the kernel trick with any algorithm you want, right? But you're going to be operating in the high dimensional space of the kernel, right? So when we did polynomial regression, we went from a one-dimensional vector to a, whatever, a ninth dimensional vector, right? Okay, so we were operating in the 9-dimensional space. And this is easy and not a problem, right? But the thing is that when we go to large numbers of dimensions and then we expand even further into 9, that same large number, that 100 or that 1,000 dimensions into 1,000 to the 9th power dimensions, that can very quickly become overwhelming computationally.
Mhm.
So the unique thing about support vector machines is that in support vector machines, the kernel trick has this particular formulation because of the Lagrangian, where we can make it not about the number of dimensions in the data, but we can make it every pair of samples. And if every pair of samples is a much smaller number than 1,000 to the 9th power, or whatever we're talking about in the polynomial expansion,
Mm.
then this is the right way to handle it, right? This can be a much easier computational problem. Okay,
Mhm.
Pete. So we will have more time to talk about this later. I have to go because I'm 6 minutes late to another meeting, but please come up with more formulations of the things that are the questions that are bothering you, and we will go ahead and discuss this more next time. Okay.
Thank you.
All right. Bye, everybody.